introduce ourselves so you know who is who in case you don't. And we will have initial sip of Slivovica. I am Vid, Martin Mocko. So, here you go.
Thank you, sir. I'm Tom Tobias.
And I'm Futter.
I'm Ferino.
I'm Manis. Hi, I'm Medjan Lutekasi.
And I am Hypervista. Hi, Ali.
And once again, me, Thomas Gristar. Hello, everyone.
Do you want to announce the
Yes.
speakers? Why don't you announce all the speakers?
Okay, so first one to present will be Tom with his custom design of processor.
Why don't you write down the board so everybody can see?
I don't know his name, you do. Okay. Go on.
I'll be the first one talking. And that's because we need to get some of the bugs out of our hardware and software. It's better to do that with this talk than any other. Thomas has given you a welcome, and I would like to add to his remarks for those of you who are watching this broadcast and also for those of you in this room. I'd like to extend my gratitude, which I think all of us feel, to both Mazegen and Hypervista for the excellent job they have done these past 3 days organizing this FASM conference. And we are all grateful to you both. Now, assembly language programmers are fond of saying, correctly so in my opinion, that one of the advantages of assembly language programming is an opportunity for an intimate relationship with the hardware, the CPU, and the other motherboard components. This is certainly true. What I would like to do now is to give you a quote. I'm not going to ask you who made the quote, but I am going to ask you to guess when this quote was issued. Our appetite for computing power is insatiable. Does everyone know what insatiable means? It means you cannot quench the thirst. No matter how much Pilsner or Quell you drink, you still need more.
Yeah, I know that.
Standing on the threshold of the 5th generation, we clearly expect more from future computers than just more speed. Can anyone give me a suggestion as to when this quote was made?
1960.
Good guess, but wrong. I'll read it again. Our appetite for computing power is insatiable. Standing on the threshold of the 5th generation, we clearly expect more from future computers than just speed. No ideas? The 5th generation was the title of a book that came out in the middle 1980s. And this was from 1987. And I want to show you now some computer hardware from 1987. I don't know if this will show up on the camera or not. In 1987, that's the year of the BIOS on this motherboard. This motherboard was in the state of the art, the best computers available for home and business use. Of course, there were much larger computers in commercial enterprises, but for standard, ordinary, conventional computer programming such as that which we associate with FASM, this motherboard from 1987 was the best available. And what I want to show you on this motherboard, this is the same year as this quote from 1987. 20 years ago today. 20 years ago today. What I want to show you from this motherboard is how much memory it contains. Do you see all these slots here? This motherboard could hold 16 megabytes of memory, which, remember, was 15 megabytes more than anyone could use, because everyone was writing programs in those days for DOS, and that was a 1 megabyte restriction. So this was really an outstanding motherboard of its era. What do we think today when we look at this piece of hardware?
Antique.
That's polite. Antique is a polite answer. I think junk. Where is the nearest trash bin that we can throw this away? We actually can't throw it away because of the arsenic and gold and lead, so we can't just throw it away. We have to dispose of it properly, but it is useless, right? We all agree with that. 1987. Well, here comes another motherboard. This one now, made a few years later. It has a socket 370. And what I want to show you here is this motherboard has a memory controller that is modern. By that I mean it takes in memory 64 bits at a time, unlike this motherboard, which took memory in 32 bits at a time. 64 bits at a time for the memory controller. And how much memory will it hold? Up to 4 gigabytes. So then the question is, what goes into this socket here? Now I want you to imagine a FASM conference from 1987. We're in 1987, and Tom comes to the FASM conference, uninvited as usual, and proposes to everyone there that we stop working with DOS and with Intel, and that instead we build our own CPU, one that will go into this kind of a socket and will access the full 4 gigabytes of memory. People here would all go boo, no interest. And the reason is because it's this thing that goes in here, the CPU itself, not compatible with the existing architecture made by Intel. And that's really what my talk is about. Different kind of a CPU architecture, and does it make any sense, and what would be the value in it, and why should anyone in this room care about such a thing? I won't speak a lot longer, about 5 more minutes, and then we'll have time for some discussion, if there is any. If not, we may be able to install something that will allow us to play a hook. We'll see. There may not be that opportunity, but if there is, we've got the hook ready. The main point here that I'm trying to communicate today is this. When we look at this old hardware, we say to ourselves, that was junk. We look at our software, which dates from the same era, and we don't see that it is also just as old and obsolete. On the FASM board recently, there was a long heated debate about C compilers this, C compilers that. With the new design of the CPU I'm talking about, there would be no C compiler. It would be only written in assembly language, that's all. This new design CPU would go into that socket that we saw, the 370 socket, and it would have 4 towers, one on each corner. Anyone like to hazard a guess as to what's in these 4 corners?
Input and output.
That's a good idea. Honest, you have a lot of good ideas. Anybody else have another idea? Have you seen a modern motherboard? What does a modern motherboard look like? It has the CPU, of course, and the memory, but what else does every modern motherboard have on top of the CPU?
Cooler.
A cooling device! Is that what these 4 things are, cooling devices? No. No, they're not.
CPU cores.
Sorry to interrupt you, please use a black marker, and regarding it's not very good see.
Yeah, but the talk isn't very good either, so at least the color matches the talk.
Okay.
That's bad.
It may be that these windows being open was not a good idea, who knows? No, these 4 pedestals sticking up are receptacles for flash memory. 4 gigabytes in each. For the 4 CPUs that lie underneath each of these, and the 5th CPU here has no tower. This is the CPU that communicates with the memory on the motherboard. So the new design has 5 CPUs, one of which accesses the motherboard. The other 4 access flash memory, 4 gigabytes each. And how are these programmed? These are programmed with an ordinary USB connector to a regular IBM type computer that puts into here what kind of information? It puts all floating point data. All multiplications, logarithms, transcendental functions. So if you want to calculate the sine of 41 degrees, there's no processing computing here. It's all a lookup table. And the amount of storage available, 16 gigabytes, will certainly hold all of the transcendental data up to a reasonable size. And most of the computing that's done in the modern world, in the industrial world, in the world of business and healthcare and universities and so on, most people don't need terabytes of memory and data. 64 bits is more than adequate to represent most integer values that are in common use. And so the new CPU architecture would have 2 major differences from the von Neumann architecture that we find out here today. There would be only a few instructions, about 10 instructions total. And there would be no more memory bottleneck like with the von Neumann architecture, because now each of the different CPUs has its own access to flash memory. So let's review some of the possible instructions. What about everyone in this room is used to thinking of a stack? Am I right?
Yes.
Is there anyone who doesn't use a stack? To me, when I see a stack, I'm not thinking of this motherboard. I'm thinking of the one that came before this. Because the idea of a stack, we're talking 1950s. Why do we need a stack? What's a stack for? A stack is just a place in memory for addresses. It's a convenient shorthand way of keeping track of addresses. So there's no more stack. What about in and out? how can you access the motherboard?
You could do memory mapped addresses instead. That's smart.
Exactly right. All memory mapped. And what about multiply signed or add signed or unsigned? No, none of that. That's implementation dependent. 64 bits only. 64 bits means it's up to the programmer to decide how he or she will keep track of this data. One data type. Not strings, characters, integers, floating points, just one. 64 bits. You want to represent only a Boolean, yes or no? Use the whole 64 bits. Isn't that wasteful? We're squandering all that memory. Memory is free. The idea here is to get away from the 1950s and 1960s and 1970s, and even as late as 1990, the people promoting the ARM, reduced instruction set computer, argued that we needed to be conserving memory, saving memory. There is no such need in the modern time. So the new CPU design would have only one data type. What about different addressing modes? How many different addressing modes do we need? Well, I bet every one of you is using at least 5 or 6, right? Base point, power, some kind of informal redirection and indirection based upon a pointer going to another pointer. How can you possibly write a computer program without indirection? Only direct. All right, well, I've tried to give you some controversial, challenging ideas. I have a small list of some additional instructions that might be useful in such a new device. About 12 altogether: branch and clear interrupts, set interrupts, and 3 Boolean instructions, and, not, and or. And those of you who are convinced that the only way to clear a register is with exclusive OR, you can make your own little function, XOR, from those Booleans, and you can do that instead of move register 0 as you like. And there's add and subtract, shift and right and shift left, and test. I think there's about a dozen instructions that are needed for the new CPU. 1 data type, 1 addressing type, and 32 gigabytes of flash memory with all of the floating point computations performed, and all arithmetic and mathematical operations become lookup tables instead of...
The problem is that flash memory is extremely slow at this point in time. So we'd have to develop a new type of flash memory. I know there's some research going on that, but it's still quite some way until it's in production.
Well,
so flash memory is dozens of times slower than regular memory types.
It may be that with simulation studies of such an architecture, there would be a lot of problems that show up. Maybe that's not the only one. Maybe there's a whole bunch of other problems to emerge. The next step, obviously, is for me to make a simulation and find out just what kind of problems arise.
In case those tables are constant, you could also use some EPROM, read-only memory.
Yes,
Or
but the problem with that is that now you need a second layer on the CPU chip to hold the sockets for the EPROMs to go into, and that means the second layer, which sits on top of the CPU, has to also have 32 bits, or really 64 bits, because the memory is 64 bits wide. You have to have 64 wires for each CPU on top of this card. It becomes a multi-layer card, and that becomes prohibitively expensive. Whereas just having the sockets to the EPROM is very inexpensive. Anyone else like to challenge, ask a question, or?
I have one.
Yes?
My problem is that if there is only direct addressing mode, then
Yeah.
how would we do the lookup in the table?
By the operand. The operand serves as the address. And that is dependent upon the programming of the IBM computer that makes the flash memory in the first place. There will have to be an offset. For example, the offset from the beginning to where the logarithms start. And then the logarithms start and they go sequentially in order in terms of the value of the operand. And that's a question of having synchrony between the programming of the flash memory and then taking it out of the IBM computer, plugging it over here to this one, and making sure that when we write our programs, we use that offset. And there'll be offsets for each of the different categories.
But this is in fact very similar to indirect addressing.
The difference is the CPU design itself, it becomes simpler. Because now, let's say that we want to build such a device. The number of gates, logic gates, needed to construct in silicon such a device is greatly reduced when we have very few instructions, very few addressing modes. The complexity of the Intel architecture is made possible by virtue of the fact that they can pack so many transistors in such a small space. That's where all the heat comes from. We won't have any heat because we won't have that many transistors. This is going to be a very, very primitive design. All of the sophistication comes from the programmer's effort. And it's all done in assembly. There won't be any compilers for this.
But you won't be supporting any kind of indirection, not even the reduced design thing.
As soon as a person needs indirection, it's the same as if they need exclusive OR. You say, well, wait a minute, you haven't given me exclusive OR. That's right, but you can make it, can't you? You can make it from using a Boolean function or a Boolean function not. You can do it.
Yeah.
And so, the point is it can be done. It's just limiting as much as possible the total quantity of instructions and making sure that the data appears in those USB flash memories.
So one of the main goals of the system isn't to achieve speed, because having to construct things like exclusive OR from two instructions would make it slower.
Slower than the Dickens. Remember, 90% of the computers that are used in the world don't need fast Intel CPUs. But what I'm saying is if you look at these old motherboards and look at the tremendous improvements we've made in these old motherboards, where is the comparable improvement in our software? I don't think it exists. I think that we're still stuck with the ideas from the past. Anybody else want to add anything? If not, I'm going to turn it back to Vid to introduce our next speaker.
I would just like to note one thought. Even if it would not be faster in any way than any architecture that is used now, I think that this has the advantage that it would be much less power consuming.
Oh, much less. Much less. And one more advantage, much easier to learn. Because we're talking about 12 instructions, one addressing mode. This will be much easier than learning C. This will be elementary. Every 7, 8, 9-year-old kid can learn this. This is
The
not.
instructions will be very simple, but constructing something on it will be somewhat harder, because you have to break everything down into very small bits. So you have an advantage on the x86 that you have some instructions that make it shorter and easier to construct programs. But it's going to be easy to adjust instructions of the computer.
You want to introduce the next speaker?
Shall
Go.
this? You open companies?